Right, ladies and gents. So we're continuing on with probability from last week, and in today's session, we're going to revisit the binomial expansion by Pascal's triangle, have a look at the binomial series and the formula method of the binomial expansion, and then we'll feed that into looking at the binomial distribution and how that can be used in some examples or an example from industrial inspection. So the binomial distribution is all about choices between options. We had a little bit of a look at this last week. So binomial expression is one which contains two terms connected by a plus or a minus sign. Examples include p plus q, a plus x all squared, 2x plus y all cubed, and so on. So if we expand expressions of brackets a plus x, close brackets to the power of n, for integer values of n from 0 to 6, we get the results shown there. Okay, so we had a look at that last week and how they expand. I'm just going to go through that again to show you how that works. Right, on the next slide, this is what we covered last week. So as an example, showing you where all that comes from. If we expand ax to the 3, a plus x all to the power of 3, this one, what we're doing is we're taking each bracket term and multiplying it by, and doing that 3 times. So the first thing we do is expand these first pair of brackets. So these two. So a times a gives us a squared. A times x is ax. X times a, but we write it as ax, so it looks the same. Keep them in order. And then lastly, x times x is x squared. And then we can draw these two like terms in the middle here together to get a squared plus 2ax plus x squared. And if we look back at the triangle, that's what we have here for a plus x squared. What we then do is to expand it to a plus x all cubed. We then multiply the red brackets by the final a plus x term. All right. So we're multiplying a squared by a to get a cubed. We're multiplying a squared by x to get a squared x. We're multiplying 2ax by a to get 2a squared x. We're multiplying 2ax by x to get 2ax squared. And then we're multiplying x squared by a to get ax squared. And lastly, x squared by x to get x cubed. Can then draw the two light yellow terms, these two, together to make 3ax a squared x, and draw the two green light terms together to make 3ax squared. And that is shown, so we're looking at a cubed plus 3a squared x plus 3ax squared plus x cubed. And if we look back at the table, you'll see that that's what we've got right there. Okay, everyone okay with that so far? And that if we carried on multiplying the previous term by a plus x, we'd get this table build up as shown on that slide. Everyone happy with that?
Yeah.
Yeah.
Please say so if not. Okay. Now, what we can do about looking at that results from multiplying the successive terms, there's some things that we can note about this triangle shape here, and they are that if we look at the index of A, and we'll just take the third line of the A to the 3 column, the index of A reduces by 1 as we move from left to right across here. So we've got 3, 2, 1, and then there's no A term at all. So the index of A decreases in power from left to right. We can also note that the index of X increases as we move from left to right. So we got x to the 1, no x in the first term, x to the 1, x to the 2, x to the 3, x to the 4. Okay, if we take a line down the middle terms, down here, you can see if we look at a line where there's an odd number of terms in it, like the fourth A to the 4 line here, we can see that either side of that yellow line I put on, we've got 4 and 4 either side. The coefficients symmetrical either side. On the bottom line here, we've got 15 and 15, 6 and 6, symmetrical about that center line. On a line where, like the fifth A to the 5 one, we've got 10 and 10 either side and 5 and 5 either side of that. So the coefficients about the center line are symmetrical. Okay. Furthermore, if we take just the coefficients, as we've done in this table here, we get Pascal's triangle. And what we can do with Pascal's triangle is always find the next line in the table by adding pairs of numbers above it together. So if we look at this third line in the table, we know that 1 always appears on all the outside terms. So the coefficient is always 1 on the outside on both the left and right hand side. If we've got this line here for A plus x to the 3, we can get this coefficient by adding, so we can get this coefficient by adding the two numbers above it together. 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4. 6 and 4 is 10, 6 and 4 is 10. Yep. 1 and 4 is 5. So you can build up a Pascal's triangle using that method. Okay, now that method to find a binomial expansion will be okay up for a value of n of around 10. Beyond that, you'd be getting a little bit unwieldy. You won't be asked to do anything up beyond 9 or 10, power of 9 or 10. Okay, so Pascal's triangle is one method of being able to find the coefficients of each term in the binomial series. Everybody okay with that?
Yeah.
Yep.
Yeah. So, for example, if we want to expand A plus x to the 7, we need to build the 7th line in the table, which we can do from these. So we have 1 and 6 to make 7, 6 and 5 to make 21, and so on there. And then we can write out the expansion. So A plus x to the 7 we know it's going to start with a on the left-hand side. That's going to start to the power of n. Then we take this coefficient 7, and we take 1 off the index of a, because we know it reduces by 1 as we go from left to right, and we add a term in x. Then we put the 21 in, and we reduce a index again to 5, and we make x to the power 2. Then 35 comes down to here, a to the 4, x to the 3. 35 again, a to the 3, x to the 4, and so on until we get to the last term, which is going to be x to the 7. So it's not particularly difficult to find these coefficients. What we're going to be doing with this is using it to find the probabilities of different numbers of terms when we got a choice. So let's think about if we tossed a coin, it's a heads or tails choice 5 times. One end will be the probability that you can get 5 heads. The other end will be the probability that you can get 5 tails. And then the others in between are 1 head and 4 tails, 2 heads and 3 tails, and so on. Okay, so we'll be looking at that shortly. Everybody okay with being able to build or expand that binomial expression into a series using Pascal's triangle? All okay with that?
Yeah.
Yeah, good. Please shout if not. Nice and loud. Okay. What I want you to do then is determine using Pascal's triangle the expansion of a plus x to the power 4. And for expansion down to 4, it wouldn't actually take that long to build the triangle. We know we got 1 at the top. And then the second one is 1 and 1 either side. We then know we got 1, 1, and 2. 1 at the side, 3, 3, and 1. 1, 4. 6, 4, 1, and that's for a plus x to the 4. So now you can then from that you can write your expression. Right, who's got an expression for me then?
A plus x cubed to the 5.
So that's a plus x cubed all to the 5?
Yeah.
Like that. Because what we're looking to do is take each of those coefficients and say it's 1 times a to the 4, no x term because x is to the 0 on the other side, plus 4 a to the 3 x. So they come from that one, that one from gives us that one. Yeah. Can you carry that on now?
Hang on, just quickly, Mike. We're doing the 5th line down here. I thought, oh, are we not meant to be doing the 4th line down?
No, this is a plus x to the o as the top one. A plus x to the 1. Yeah.
Okay. Yeah.
A plus x to the 2, to the 3, to the 4. Right, who's got the next term for me?
6a squared x squared.
Yeah, a 6.
A to
Take
the
1 off
2.
the index a, add 1 to the index of x.
Yeah.
So that comes from there, that's 6. Yeah.
Yeah.
And the next one?
4a x cubed.
4a. Yeah, we took 1 off the index of a, add 1 to the index of x. Yeah. And that one comes from that 4 there. And then lastly, we have
Just x to the power of 4.
x to the 4, because the a becomes to the power of 0, which means it disappears, becomes 1
Yeah.
effectively. Yeah. So that last bit comes from the 1 on the end. Okay. So if we had enough lines in our table of Pascal's triangle, we could build any expansion and find out the value of any particular term, first, second, third, fourth, 5th terms in that particular expansion. Yeah. Everyone happy with that?
Yeah.
Yeah, all good, thank you.
Good.
Shouldn't we have had a to the 5 and 5a cubed x 6a squared x squared 6 and then 10ax?
Sorry, Christian, shouldn't you, why would you have a to the 5?
Because we're doing it a plus x cubed to the 5.
No. I aren't sure where you got where this come from.
I thought you just wanted an example.
No, what I wanted you to do was use this table, this Pascal's triangle, to build this expression. So we take this coefficient, a to the 4, because we're doing a plus x to the 4, the highest power we're going to have is 4. Yeah. And then we take this one from here. We take 1 off the index of a, so we make it 4 minus 1 is 3. We add 1 to the index of x. Well, the index of x in this first term is effectively x to the 0. Any number to the power of 0 is 1. So we don't even, it hasn't got an x term, so we bring x into play. Then the next term, 6 comes down. Yeah. We take another 1 off the index of a and add 1 to the index of x. And then this term comes from here. 1 off the index of a, so it's a to the 1, x to the 3, and then the last term has just x to the 4. Yeah, I'm not sure where this come from.
I was just trying to make it so the head worked a little bit better. And to the 5, I thought you just wanted something to expand, not related to the triangle. That was all.
No, I want you to expand this expression, a plus x to the 4, using the triangle. Yeah.
Yeah, got you.
Is it kind of clear what's meant by that now? Because that's the main thing.
Yeah, sorry, I thought you just wanted an example to be able to expand. That was all.
No, I didn't. No. All right. Okay. So what we're going to have a look at now is a formula method of binomial expansion. So the binomial series or binomial theorem is a formula for raising a binomial expression to a certain power, to any power without lengthy multiplication. The general expression or general expansion for a plus x to the n is given by a plus x to the n is a to the n. So that's where we got our first term. That's always a to the power of whatever n is. Then that's n times a to the n minus 1 plus n brackets n minus 1 over 2. Now this 2 exclamation marks, does anybody know what that means? 2 exclamation mark, 3 exclamation mark.
Oh, I can't remember the name of it now.
I'll just add
The
a page,
factorial, isn't it?
Yeah, 2 exclamation mark means 2 factorial. Yeah, 3 exclamation mark, 3 factorial. Now you have a factorial button on your calculator, okay? But what 2 factorial means is, what factorial means is every number up to that number 2 multiplied together. So 2 factorial is 1 times 2. 3 factorial is 1 times 2 times 3, which is 6. 4 factorial, 1 times 2 times 3 times 4. 24. Yeah, so that's what that means, factorial. All right, so that series expansion can be carried on for any number of terms. Now, what I've done is highlighted in red where the coefficients come from that we were finding using Pascal's triangle. So the first coefficient here is always 1. The second coefficient is n. The third coefficient comes from this. The third coefficient from that. And that pattern could carry on for as long as you like. Okay. So what we'll do on the next slide is just take a look at how that can expand the same expression that we've just expanded, a plus x all to the power of 4. So we're going to expand a plus x to the 4. So in the formula that you've just seen, we add in the coefficients. So that one's n, that's 1, that's n to the n minus 1 over 2 factorial. That would give us the first term. And 4 minus 1, 4 minus 2 over 3 factorial. And this would give us the next coefficient. And then lastly, we have the final term on the end. Okay, so when we start to simplify those, okay, we get 1. That comes, and then just let me change my color. That 1 comes from there. That 4 comes from there. 4 times, this is 4 times 3. 4 times 3 on the top. 2 factorial is 1 times 2. We have 4 times 3 times 2 over 3 factorial, and 4 times 3 times 2 times 1 over 4 factorial. Yeah. And then if we solve all of these in red, 1, 2, 3, we get these 4 divided by, sorry, this is 4 times 3 is 12 divided by, hang on, 3 4s are 12, 2, that gives me 6. Ah, no, here's the 4. This has got to give me 6. So that one gives me that 6 there. That one, 4 times 3 times 2 over 2 times 3. That 1 in there as well. Isn't it? So that's 6 on the bottom. 3 4s are 12, 24. 24 over 6 is 4. So that gives me that 4 there. And we've got 4 times 3 times 2 times 1 on the top, 4 times 3 times 2 times 1 on the bottom. Divide that out, that gives me 1. So there's where our coefficients come from. Okay. Now, certainly that looks quite confusing, perhaps at first glance. But if we are only interested in one term of a lengthy expansion, let's say this term of a lengthy expansion, we can just plug that in to the relevant section of the formula and get that coefficient. We can plug in the values into the relevant there or there or there part of that formula and find the coefficient. We don't necessarily need the whole expansion. If we had, for example, a plus x to the 13, but we were only interested in the 5th or the 6th term, we could use this formula just to find that one term, rather than try and build up a big Pascal's triangle to find that one term. Okay. So, using the formula method, determine the 3rd and the 4th terms of the expansion a plus x to the power of 8. So we'll do that together. The 3rd, we'll do the 3rd term together, and then we can have a go at doing the 4th term. So the 3rd term is given by n minus 1 over 2 factorial I to the n minus 2 x squared. that would give us the third term. All right. So what we need to do, we're trying to find ax to the 8. So n is equal to 8. Yeah. So if we replace n with 8 in that formula, we get this. 8 minus 1 over 2 factorial I to the 8 minus 2 x squared. Yeah. That equals, this bit on the top here is 8 times 7. 7 eighths are 56. And on the bottom, 2 factorial is 2. I to the 6 x squared equals 28 I to the 6 x squared. Okay, so that comes from the third term that's the third term in the series. If we look back, the third term in the series is given by n. This is the first, second, third term. Fourth term in the series is given by that. So you see if you can work out what the fourth term is using the formula, that being the formula. Right, what's that the fourth term then? So given by,
Would it be 56 a to the 5 x to the 3?
That's what I got.
yeah, you are correct. Well done. So it comes from n, I've got an uncover there, n to the n minus 1, n minus 2. So this is where the coefficient comes from, over 3 factorial. So we got 8 times 7 times 6 on the top, over 6 on the bottom. Yeah, and 7 eighths are 56. So it becomes 56. Take 1 off the index of A to make it 5. Add 1 on the index of X to make it 3. So that's your answer. Okay. And as this checking using Pascal's triangle, we can see that the formula is as for AX to the 8 gives 28 and 56 in that position. I haven't done them all. We had 7 and 21 together to make 28. We had 21 and 35 together to make 56. Okay. Everybody happy with that? Now,
Yep.
I believe in the assignment problem around this teaching that I'm doing today, I've given the option to use either the formula or the Pascal's triangle method when you need to find an expansion. So the choice there will be yours. Okay. Let's have a look now at where that's relevant to probability. So the binomial distribution. This deals with two numbers only, these being the probability that the event will happen, P, yeah, and the probability that the same event will not happen, Q. Yeah. So if we're talking about a coin being tossed, P could be the probability that it will end up heads up, and Q is the probability that it won't land heads up or it'll land tail up. Yeah, not heads up. So P is that something will happen. Q is that that same thing will not happen. It's a binary choice, one or the other. Yep. Binomial distribution can be used for finding, say, the probability of getting 3 heads in 7 tosses of a coin, or in industry for determining defect rates as a result of sampling. One way of defining a binomial distribution is as follows. If P is the probability of an event happening, and Q is the probability that it will not happen, then the probabilities of that event happening none, 1, 2, 3, or up to n times in n trials are given by the value of the successive terms of the expansion of Q plus P to the n, taken from left to right. You'll notice that the probability of it not happening is first in that binomial expression. It's Q plus P, not P plus Q. So if we look at that expansion from earlier, if we're talking about the toss of a coin, this would be the probability of you getting tails n times. This would be 1 heads, the remainder tails. This 2 heads and the remainder tails, and so on, 3 heads and remainder tails. Yeah. So as we go from left to right, it's no chances, 1 chance, 2 chance, 3 chance, and so on. 3 times, sorry. So let's have a look at a particular example. Determine the probability of having at least 1 girl and B, at least 1 girl and 1 boy in a family of 4 children, assuming equal probability of male and female at birth. Yeah. So if what we're saying here is the probability of a girl is P. So we'll let P probability of a girl and P is equal to, if there's equal probability, 0.5. Agreed? Q probability not a girl, i.e. a boy. Yeah. Q is also equal to 0.5. So we got our 2 probabilities, and in this case, they are equal, like the toss of a coin. If it's a fair coin, is equal. Okay. Now, our expansion, what is n in this particular? What's the value of n in this particular problem?
Four.
Yeah, it's the number of children, 4. Yeah. Now looking back at so what we need to do is we need to expand q plus p to the power of 4. All right? And if you look at your Pascal's triangle, we'll use that method. It's equal to q to the 4 plus 4 q. I better put this on a new line. I'll not fit it on. It's equal to q to the 4 plus 4 q to the 3 p plus 6 q to the 2 p squared plus 4 q p cubed plus p to the 4. Everybody was happy with that, but that comes from the expansions that we've been looking at. It's just that we've changed from a plus x to q plus p.
Could you just tell me again why it's not p plus q? And would you get the wrong answer if you did do p plus q to the 4?
What the reason you want it to be q plus p, Lewis, well, all of you, is that you want the left-hand term to be, just let me, you want the left-hand to be 0 girls, because the p is the probability of a girl. So this is 0 girls, 1 girl, 2 girls, 3 girls, 4 girls. Yeah. So you always want to start with there being none of the chance that you make p. So p is the probability of girls, and to keep it in order, you want it to go 0 chance, 1 chance, 2 chance, 3 chance, 4 chance, and so on from left to right. If you put the expansion the other way around, if you put it to p plus q, 0 girls would be at the right-hand end, wouldn't it? All happy or not?
Yeah, I'm not gonna
Lisa,
lie, I'm lost.
you're lost, Kirsty,
Yeah.
are you? Okay. Let me try and repeat. We've got the probability of a child in this family, be it a girl, is p. Yeah. The question says we're assuming there's equal probability of male or female at birth. Yeah. So that p probability is 0.5. Therefore, the probability of at birth being a boy is q. That's in terms of this these probabilities. That's the probability of it not being a girl. That's q. Yeah. So remember, when we say and in probabilities, the problem of the first and the second and the third and the fourth child not being a girl is that 0.5 multiplied together 4 times this q to the 4 here. That's building on from last week. Yeah. So that's the probability of it not being a girl 4 times. This is probability of 1 girl. We got p in there once. Probability of 2 girls, 3 girls, 4 girls. Does that help?
A little bit. I think I just need to kind of practice it.
Yeah, I think if we'll finish off the problem and then you might kind of see where it all fits together, because hang on. Just put that on a new page. I understand that's perhaps not one of the easiest topics to get, but so the question wants to know, right, for part A, what's the probability of having at least one girl? Okay, so at least one girl means we want this one, this probability, and that one, and that one, and that one, all added together, because they're all got at least one girl in them. Okay, now there's two ways of doing that. The first is we say we write out the whole expression. Let's just go in blue here. We say probability of at least one girl equals 4 times Q, 0.5. I'm looking at this expression here, cubed, times P, which is 0.5. So that's the probability of one girl, plus the probability of two girls, because that's got at least one girl. So 6, 0.5 squared, plus 0.5 squared. We want this term because it's got 3 girls, so that's plus 4 times 0.5 times 0.5 cubed, plus the last term because it's all girls, so we want 0.5 to the power of 4. Yep.
Have you left the first term out for a reason? 0 girls?
Yeah, but that's because that's no girls, Lewis, and we want at least one girl.
Okay, yeah, I get you.
Yeah. Okay, so this one, hang on, let's just change the color again. It's still green. Right, this one is one girl. This one is 2 girls. This one is for 3 girls. And this bit is for 4 girls. Yeah. If we add all them together, what do we get?
Sorry, Mike. On the 2 girls term, I don't think there should be a plus between the two 0.5s.
No, there shouldn't. You're right. There, yeah?
That's the one.
What you should get here is 0.25 first term plus 0.375 plus 0.25 plus 0.0625, and all that adds up to 0.9375 as the probability of having at least one girl in that family. Can anyone think back to what we covered last week, to a method that would look much easier? What's significant fact about all those probabilities that would help us here? Think of what's the significant fact of all 5 probabilities? No girls, 1 girl, 2 girls, 3 girls, or 4.
The standard deviation of
No, it's not that. No.
They all add up to 1.
They do. All of these probabilities, no girls, 1 girl, 2 girls, 3 girls, 4 girls, all add up to 1. So if instead we did probability of 4 girls, of at least 1 girl, we know equals 1 minus the probability of no girls. Yeah. So that would be 1 minus the probability of no girls is q to the 4 equals 1 minus 0.5 to the 4 equals 0.9375, which is the same answer. Okay, so sometimes that's handy to remember that all of these have to add up to 1, and therefore you might be able to get the answer a little bit quicker that way. Yeah. Everybody understand that?
yeah.
So successive terms gives you successive different chances of the same thing. So it's like throwing a dice 5 times or tossing a coin 6 times or whatever. Yeah. We start off with having no times that you get a particular result. 1 time, 2 times, 3 times, 4 times successively across that expansion. And the second part of the question was, what's the probability of at least 1 girl and 1 boy? Yeah. So how could we do that? Just take this expansion again. Put it on a new page. Which terms do we need to add together to get for it to be the probability of at least 1 girl and at least 1 boy?
First 2.
This has got 4 boys, but no girls. So we don't want that one, do we? This is 3 boys and 1 girl. We'll add that one. 2 girls, 2 boys. We'll have that one. 3 girls and 1 boy. We'll have that one. 4 girls, no boys. We don't want that one. Yeah. So probability of at least 1 boy and 1 girl equals. And there's 2 ways to go about it. We can add these 3 middle ones together. 4q cubed p plus 6q squared p squared plus 4q p cubed. Or we can add the two outside ones together and take them off 1, or 1 minus q to the 4 plus p to the 4 is an alternative method. All right. And if you do that either way, you should get 0.8750. Okay. All reasonably happy with that?
I think so.
Yeah.
Yeah.
I didn't quite get the simplify bit.
Oh, what, the second one? This method, Christian?
Yeah. Yeah.
Where that comes from is you have to remember that if we take, always remember that if we take all these probabilities, all 6 of them, 5 of them, sorry, 1, 2, 3, 4, 5, we take all those terms and add them all up. They have to equal 1. Yeah?
Yes, I got you now, yeah.
So to get these 3 added together, the middle 3, we can add them all up like that. Or we can say that that middle bit is 1, take away the outside 2, added together. Yeah. Makes absolutely no difference which way you do it. You should get the same answer. And it's always worth realizing that one is a check of the other. Yeah. I'm a bit happier now, Christian. Is that okay?
Yes, fine, yeah.
Good. Everyone else happy?
Yep.
Yeah, good. You all right with that, Kirsty? Because you said you was a little bit confused with the last bit. Is that a bit clearer now?
A little bit. I think I just need to go over it a couple of times to get it in my head.
Yeah, we're going to have a look at another example now that's kind of related to a more industrial situation. So in industrial inspection, P is often used as the probability that a component is defective, and Q, the probability that the component is not defective or satisfactory. In this case, the binomial distribution can be defined as the probabilities that an event will happen, none, 1, 2, 3, n components drawn at random from a large batch of components are given by the value of successive terms of the expansion Q plus P to the n, taken from left to right. So if going from left to right, terms in your expression now is that there will be no failures, 1 failure, 2 failure, 3 failures, 4 failures, and so on from n random samples from a box. Okay, so let's have a look at the problem. A machine is producing a large number of bolts automatically. In a box of these bolts, 95% are within the allowable tolerance values with respect to diameter. The remainder being outside of the diameter tolerance values. 7 bolts are drawn at random from the box. Determine the probabilities that A, 2, and B, more than 2 of the 7 bolts are outside the diameter tolerance values. So looking at that question, we've got to make a binomial expansion. Remember what we said on the previous slide? P has used the probability of a component as defective, Q being the probability that it's good. So in this problem, what would you say P is equal to? What would you say Q is equal to? And what would you say N is equal to? P is faulty.
So is that 0.05 or?
Yeah. P is defective, yet Q is satisfactory. So P, yeah, is equal to 5%, 0.05. Yeah. Therefore, they both got to add up to 1. So Q must be 0.95, the 95% that are good. Yeah. And what is N in this particular problem?
Is it 2?
7.
Okay.
Who said 7 and why?
Oh yeah.
TJ, and it says 7 bolts are drawn at random from the box.
Yeah,
So there's
7.
7 boxes.
Oh, yeah.
The number of bolts drawn at random. Yeah. So we need to expand what expression? Q plus P to the power what?
7.
7. Yeah. All right. So we need an expansion for Q plus P to the 7. How would we like to get that? Formula or Pascal's triangle? What would you use?
Triangle.
Yeah.
Yeah.
First thing we know is it's going to start off as Q to the 7, don't we? That's going to be our first term. Yeah. So that's 1. We need to find the Pascal's triangle now, don't we? Let's have a look. See if I can find one with the 7th one on it. I think is here somewhere. Yeah, there we go. We did it earlier. Okay. So our coefficients are 7, 21, 235s. Yeah. 7, 21, and 235s. And then it goes back from there. So that's plus 7, Q to the 6, P, plus 21, Q to the 5, P squared, plus 35, Q to the 4, P cubed, plus 35, P to the 5, Q squared, plus 21, P to the 6, Q. I've gone along somewhere, haven't I?
Yeah, on the second 35 term. You went up.
Where's that?
You've
That
gone-
should be. Oh, I
should-
read it.
U to the
Bit
3.
of P and the Q the wrong way round for a start. So that's Q to the 3, P to the 4. Q to the 2, P to the 5, plus 7, Q to the 4,
The 1, yeah.
Q to the 3, Q q to the 2, 7q, p to the 6. Plus p to the 7. Yeah.
Yeah.
All right. And these terms are 0 faulty, 1 faulty, 2 faulty, 3 faulty, 4 faulty, 5 faulty, 6 faulty, 7 faulty, from the random 7 drawn from the box. Yeah. Everybody understand that?
Yeah.
So determine the probabilities that I, 2, so this is like I said, none faulty, 1 faulty, 2 faulty. Yeah. So what we need here is to work out this probability, this third term for 2 faulty. Probability of 2 faulty equals 21 q to the 5 p squared. Yeah. That means 25q means 21 times the probability of it being good, and anyway, so we got to write 21 times 0.5 95, sorry, I'm back on the coins again, to the 5 times 0.05 to the 2. Yeah. Just put that in your calculators and give me a result.
Is it 0.04?
Yeah, what I've got is 0.0406. Yeah.
Yeah.
That's what I got.
That's the result I've got in the solution. Okay. So how can we find out, part B, the probability that more than 2 of the 7 volts are outside the diameter tolerance values?
Wouldn't you have to do the 3rd term plus the 4th term plus the 5th, etc.?
That's one way. So we could add up all of these terms. The 3 faulty, 4 faulty, 5 faulty, 6 faulty, all 7 faulty. So we could add up all those terms.
Or you could do the opposite and take it away.
Or we could do 1 minus these 3 that we're just now, these 3 added together, can't we? Because that if all of the ones from 3 onwards added together, there's a probability that there's more than 3 faulty. The other 3, q to the 7, 7q to the 6p, and 21q to the 5p squared, that's 2, 1, or none faulty. So if we add them together and take them off 1, so that's the 2 ways that we could do it. And I don't necessarily think either one as a few less terms in the second method. All right, but choosing either method, you calculate me a probability of more than 2 of the 7 bolts being out of tolerance. So I'm using the 1 minus brackets q to the 7, 7q to the 6p, plus 21q to the 5p, all in brackets, taken away from one method. So we got 1 minus 0.95 to the 7, plus 7 0.95 to the 6 times 0.05, plus 21 0.95 to the 5, 0.05 to the 2, close the brackets. Plug all that in your calculator and you should get 0.0038 as the probability of there being more than 2 faulty from the 7 bolts picked. Okay? You're all happy with how that worked? Because this is the probability of none of them being faulty. This is the probability of 1 being faulty. This is the probability of 2. So more than 2 has to be 1 minus those 3 probabilities added together. Always remember that if you add them all up, they have to equal 1. And on the next page, there are a couple of further problems for you to have a go at. So concrete blocks are tested, on average 7% fail. For a batch of 9 blocks, determine probability of 3 blocks and less than 4 blocks will fail to meet the specification. And then we got it rising, so the failure rate rising to 15%. Find the probabilities that no blocks and more than 2 blocks will fail from 9. Okay, so a couple of questions for you to practice what you've been doing this morning.